Welcome back to the enclosure. In my final segment of the HVAC update video, I wanted to briefly go through the control hardware and software that is being utilized on this hydronic heating and cooling system. As previously mentioned, I'm using the DX2W EX1 air-to-water indoor module from ThermAtlantic. This is a coil heat exchanger that transfers the energy from a refrigerant set of lines to a water set of lines in this very compact 16 by 24 by 12 deep cabinet. The module is from ThermAtlantic, and it allows for communication and control via the Modbus protocol, which I'll talk about in a bit. It is also provided with a Willow Star circulator that is installed on the circuit between the buffer tank and the DX2W module. We have then mated this with a GREE heat pump. It is a DC inverter, 36,000 BTU heat pump, 24 volt. And this is a prototype mating of these two units. The GREE heat pump has an operational range of -30 to 24 Celsius in heating mode and -15 to 48 Celsius in cooling mode, and an advertised heating HSPF rating of 10 to 10.5 and a cooling SEER rating of 18 to 20. As this is the first mating of these two units, there is no overall performance ratings at this time, and we'll be trying to determine these over the next 12 to 24 months. The control of the system is via a software package from I2 Software Inc. called ControlCore Pro. This software communicates over a Modbus communication protocol and allows for the control of all parameters of any Modbus compatible device. Modbus is a data communications protocol that has become the mainstream go-to control protocol for industry. It communicates via serial cables, Ethernet, or IPS. In our case, we're using Ethernet cables between most devices. It also supports communication to and from multiple devices on a single cable daisy chain. This level of open source control allows for ultimate flexibility in the control of your hydronic heating and cooling system, something that is just not available with the proprietary systems offered by pretty much any other HVAC equipment manufacturer. Now let's go through some of the system components and how they operate in the system I've put together. At the very top of the system is the iNet server. It is the device that stores the program and allows for all communication between devices in the Modbus network. It also allows for the cloud storage of all parameter history and for remote management of the system. The controller has two COM ports. This would allow for two devices or two daisy chains of devices. If you have more than two daisy chains or two devices, you will then need a hub. And in our case, we are using the TD1204, which is a RS485 protocol hub. It has 4 COM ports. I'm using one of the COM ports for all of the thermostats in the house. I'm using another COM port for the dewpoint sensors that I have on each floor. They're all on one daisy chain. The third daisy chain is the 3 iStats or thermostats in the control cabinet. I'm using 2 for BTU monitoring, which is basically a sensor package that I've added to the system for research purposes. And then the last one is to expand the programming functionality of the system to provide extra inputs, outputs, and memory to run control programs. Finally, the last port is being used to control the Modbus capable Maxo circulator from Willow. And you can see here it has a Modbus module that's been added to it. And so basically you just have your ground and your plus and your negative that you communicate with the device. And so basically any parameter in this circulator can be read and controlled via the control software, ControlCore Pro. The device with the most control flexibility in the system is the ThermAtlantic DS2W. It has two terminal strips, one on the side for all of the internal sensors, power supplies, pressure sensors, everything needed to manage the refrigerant movement through the heat exchanger. On the front of the unit is a terminal strip for all of the field wiring. This includes the power supply to the main power supply to the unit, both 15 volts and 24 volts. The 24 volts is AC and the 15 volt is DC. It then also has terminals for all of the field temperature sensors. So we've got outdoor air temperature, buffer tank temperature. We've got the mix temperature, which is basically the temperature of the water after the mixing valve, the return temperature back to the buffer tank. Then we've got control for relays. We've got the circulation relay, which is the circulator that goes between the buffer tank and the DX2W. We have control for an auxiliary heating supply if required, or a backup heating supply if required. We do not have one. We felt we didn't need one on this project. And then it has all of the controls for the heat pump, both inputs and outputs. And then finally, it has the control for the three-way mixing valve. On the inside of this control cabinet is the Modbus capable device, which is the PMETA. And most of the terminal strip terminations that you saw earlier are all connected to this device. And basically all of the Ks are devices that action is taken on them. So they are operating something, and all of the U's are inputs like temperature sensors and pressure sensors and the like. The next device with the most control ability is obviously the thermostat. In our case, we're using iStats. They are from I2. Again, they are they have an LCD PCL control right within the unit, and then it can also be controlled through Modbus through the central controller. The terminal plates for the iStats look like this. And basically we have all of our analog inputs, which are basically the sensors, whether they be temperature, they can be pulse, and I can get into the various types that there are a little later. We have the connection of the Modbus, and then we have both analog and digital outputs. And some of these can be programmed for both as well. But these are basically the input side of things, and this is the control side of things. And basically you provide a 24 volt power supply, you jumper that down to the K-COM, that provides 24 volts to all of the K terminals, which are basically relays, and they'll open and close. That is for opening and closing the zone valves or actuators. And then these are all of, for instance, in a typical situation, all of the temperature sensors from remote rooms. So what I have set up is I have centralized iStats, and each one controls up to 5 zones. And so I have up to 4 remote temperature sensors that are in rooms that don't have an iStat, where I'm just recording the temperature in that room, and that is then used to control its corresponding actuator to open up the appropriate zone valves. The device also then has an onboard temperature sensor, which is can be used to control one of the K relays as well. While we're talking about sensors, let's also look at the dew point control. So on each floor, about a foot off the ceiling in a centralized area, I have one of the, basically they are sensors that provide the current, humidity, and temperature of that room or area. And then this is used in the code to calculate the dew points, and I'll explain why that's important in a bit. These are from Greystone, and they allow for communication via Modbus. And if we go back, you can see they have a power connection, and then it's sort of bleached out by the light, but there's the Modbus, the shield, and the plus and the negative connection here. It is the last device on the daisy chain. You have to set the end of line jumper. In this case, this one was not, but if it was, you would put the jumper across both. You can also get them where this LCD is visible through the cover. I didn't choose to get that one. And if so, you can choose whether or not it's backlit or not. But otherwise, you can read the value of these sensors via the centralized software. So going back to the system, this is prior to it totally being finished. Not all the sensors are installed at this point. Not all the wiring is complete. But basically, we've got our iNet, we've got our hub, we've got 3 of our iStats that are, as I said, BTU monitoring and extra control. We've got our DX2W, got the relay that is controlling the circuit that's going to the air intake of the HRV, and I've got a coil in that intake, and this allows for the preconditioning of air into the HRV. And I'm actually finding that I'm able to keep the output side of the coil at around 20 Celsius, even when it's 10 or 8 degrees Celsius outside. This is a BTU meter. It's sort of an overall BTU meter that we'll use for calibrating our individual BTU meters that are going to be over here. We've got our Willow Maxo panel circulator. This is what circulates the water to the ceiling panels. Got our mixing valve. So what happens is the water comes back from the panels, not as hot as it went out. So it's, say, warm water instead of hot water. It will get mixed with the water coming off the buffer tank if the temperature needed by the panels, which is going out this way, is less than what's in the buffer tank. So it allows for the buffer tank to be cycled with a reasonable on-off deadband, so we're not overtaxing the heat pump. And then we can basically ramp up or down this mixing valve to allow for a common output temperature that matches what we figure out we need based on the heating load of the house and the outdoor air temperature. And then we have, to the right of the DX2W, we've got the 105 gallon storage tank. We've got the relay controlling the circulator. This is the Willow Star supplied with the DX2W. This is the loop that goes between the DX2W, which is just off screen here, and the buffer tank. So now let's look at the actual software that is utilizing all of this. Just one thing before I go there. I was doing some testing, and I actually am embarrassed to say that I had miswired. There was something lost in translation between the time I roughed in my ceiling panels and put in the manifolds and the actuators, the zone actuators, and the time that I put in the instrumentation. I did not, for some reason, did not match those two processes up, and so I ended up miswiring a lot of my actuators. And so I let the system cool down, and then I would open one actuator at a time and use my FLIR camera to identify what zone was open. So here is a zone that was basically open for a couple of minutes, and you can see how well the temperature is flowing out and covering the surface of the ceiling. The hot water is obviously flowing in this direction. This is the hottest water coming into the system, and then it's gradually getting cooler as it goes out. So now let's look at the software package. ControlCore Pro. This is basically your opening screen. I'm going to open up the project. And this is basically what you come to. At the very top is the iNet server. Then you have the 2 ports of the iNet. And I misspoke earlier. I said that the thermostats were on one of the comms of the hub. And this is actually not true. I forgot that I rewired the thermostats to be directly connected to the iNet instead of the hub. The hub has the dew point control, the BTU meters, the mechanical iStat, which is for expanding the control availability of the system, the Willow Maxo circulator, and the DX2W. So each device is listed. You can start with the iNet, and you have the overall settings for the system, including the cloud storage. You can choose what parameters you want to store. So you would basically select each parameter. These are the dew point sensors. You don't have direct access to their parameters. You have to do it through a block, and I'll say what that is in a bit, in the iNet. But the iStats all have direct access to their parameters, as well as the DX2W. So you just basically go through and you select all of the available parameters and decide on which ones you want to keep a history of, and select all of those. And I'll show you what the history looks like in a bit. And doing the same thing for the 4 thermostats. I have 2 on the top floor, 1 on the main floor, and 1 in the basement. And you can see here we are operating 4 different zones on the T1 thermostat. We're operating 4 zones again on the T5 thermostat, 4 zones on the T11 thermostat, and 5 zones on the T15 thermostat. It'll tell you how much this is going to cost you a day based on the number of seconds that you record of each parameter. Then there's buttons that basically allow you to manage the system. So sync all project devices means that you send the programs that you've written in each device within the software to the actual device. And then you can send that overall program to the server. So basically, you use this software, you edit all of your programs within this window, you upload that program to the device itself and to the iNet server. It allows you to reboot the server, it allows you to read variables, so you can read all of your history settings that stay on the device. You can read them into the system so that you don't lose them, for instance, when you do an update, and that kind of thing. Let's get into the nitty-gritty. We'll go straight to the DX2W. You start off with, again, just a basic screen where you're setting its device address, which allows it to, each device on a Modbus network has to have a unique address, and this is similar to an IP address. Configuration page shows that PM5 ETA device, all of its available terminations, and then what each one does. So for instance, I'm going to go to this empty one. You would click here, that's an analog input, that's a digital input, and that's the two options you have for there. On the output, digital output, and that's the only option you have there. So these ones are a little bit more restricted than the INETs, which I'll show you later. Once you've set the data type for each input, then you can go in and name them and advise whether it's going to be user accessed and min accessed. Is it read only, or are you also wanting to write it? And if it's a temperature, is it going to be C or F? That will then show up on the LCD display on the actual device. So if we go back down to here, whatever you put in the parameters list is actually going to show up on this LCD here. And these buttons would allow you to scroll through the parameters, and then the middle buttons would allow you to set the settable parameters. Let's get back down to there. Once you've identified the input-output types, you've determined your parameter list that is going to show up on your LCD screen. Now you get into the actual programming of the device.
So this is the programming screen for the DX2W from ThermAtlantic. On our left, we have all of the inputs, and on our right, we have all of the outputs. These were what was defined in the terminals here. So each terminal, we defined what type of output it was, and then that shows up on each side of the program screen. And then all of this is blocks that have been selected from the available blocks above and added to create the program between reading the inputs and acting on the outputs. Now, the input and output data types differ depending on what type of device it was. So I showed you here that we only had digital output, and here we only had analog input and digital input. But if, for instance, we go to one of the iStats, we can see we've got analog input, we've got digital input, we've got counter, we've got frequency, and then off. So that allows for a lot more flexibility in what you're connecting as far as sensors and the like. And then on output, we have digital output, and that is it. Analog output or digital output. The analogs can be converted to digital. So again, it's based on the device itself. We'll have unique available data types that it's been programmed to accept and to act upon. So now let's go back to the DX2W and program page. We're going to look at what the available blocks are. So if we go to Help and Contents and maximize this so we can see it properly, and then if we go to Devices and we go to Device Programming, we are then given a list of all of the devices that are available. So we have an analog input block, counter, so this is for counting, for instance, pulses. We have a frequency input block. We have an analog output, digital input, digital output, LCD function. So this is to emulate the LCD on the front of a device. So in other words, the buttons that are on the device would appear on this. Analog value function block. And we'll, like you can see here, there's a lot of options. I haven't used the majority of them yet. I'm very new to this program, but all of them are listed in the help, and you then have all of the parameters that are available within that block. And one of the most common ones is the thermostat algorithm. So it allows you to basically create a thermostat on the fly. You're not stuck with a manufacturer's proprietary thermostat control. You are basically building it from scratch and telling the thermostat what to do based on the inputs and what to act on based on those inputs. And how to respond to internal temperatures, when to respond. In other words, how dead bands, how much do you let the temperature go above and below the set point. It's amazing the control that you have over the system based on using this ControlCore software that ThermAtlantic have incorporated into all of their devices. They've used this protocol to create the functionality of their devices, and it's just not available in any other manufacturer's products. Clock function, that's something I'm going to be looking at to act on the system based on the time of day. So for instance, I'm going to be looking at seeing how to program this so if it is a sunny day outside in the wintertime, to allow the buffer tank to chill down, in other words, don't maintain its set point temperature, and then open up zone valves in zones that are significantly over the set point. So for instance, any of the southern rooms, they can get 2, 3, 4 degrees above set point when it's sunny out, even if the heat's not on. So by opening up those zone valves, you can then extract that energy from the room into the water stream and take it back to the buffer tank. But of course, you can't do that unless the buffer tank temperature is less than the room's temperature. So I'm going to be looking at using a clock function to allow this programming to run during the sunny hours of the day. There is so many functions here. If you do get this program, you're going to have a lot of fun figuring out what you want to do. And I mean that literally. You're going to be thrilled with the functionality that if you can think of it, you can do it, basically. One of the most important blocks is the analog function block, and this is basically where you create your formulas. So you create your target temperature formula based on outdoor temperatures, and I'll show you that in a bit. And these are the operators that you can use. So you can plus, minus, multiply, divide, greater than, all that kind of stuff, not, and, or, and then highest and lowest, that kind of thing. And then you've got some higher function operators that you can use as well. And these do take some time to figure out. You might be able to do something in another program that you then have to convert to using just these available functions in this program. So I had to do that with something using log, and it took me a while to figure out the right call on how to convert everything to using log. So now let's go to one of those formulas, and let's talk about the mixing temp. So in a good system, a well-designed system, the temperature that you are maintaining in the buffer tank and in the circuit, the main circuit going to the house, is based on the difference between indoor temperature and outdoor temperature. So the colder the outside gets, the higher the heating load, therefore you require a higher heating temperature. So what I did is I went, the previous version of the formula was working, but it wasn't tight to the outdoor temperature. It didn't follow the outdoor temperature as well as I wanted to. It was following more the buffer tank temperature. And the buffer tank temperature obviously cycles up and down as the heat pump comes on and off, and you have your on dB, off dB. So let me run the program. It's just saying that I've made a change to the program. Please upload it to the device before you run the device. So let's run it now. Okay, so now the device has been updated and the program is running. And so we have an outdoor target temp for the system based on the outdoor temperature. So we've got a temperature that we want to maintain within the system based on outside temperatures. And I'll get into that. This basically means it's a remote call to another device where you see these circles. So remote analog variable, remote digital variable. So it's just saying this exists somewhere else, but we're going to call it here.
So that formula has set a target temperature of 83.3. This is based on the outdoor air temperature of 52.1 degrees Fahrenheit. I have allowed for the buffer tank temperature, which is the hot water target temperature, to be 2 degrees higher than our ceiling panel supply temperature. And I've set the on dB to 1.5 degrees and the off dB to 7 degrees. So this means that our buffer tank temperature will never drop below our target panel supply temp water temperature. And in fact, it will always be 1/2 degree above the target panel supply temperature. This means that the buffer tank will cycle between 1/2 degree above our panel ceiling panel target temperature and 7 degrees above our target temperature. So the reason this is important is that you want your mixing valve to have at minimum the temperature that is required to go to your ceiling circuits. It does not make sense to supply the mixing valve with a temperature that is below the house's current heating requirements. So the heat pump will activate when the buffer tank temperature is equal to our panel target temperature plus 2 less 1.5 degrees, and turn off when it is our target panel temperature plus 7 degrees.
And what that allows is for the heat pump to run for a reasonable amount of time and then shut off and not have to run for, in our case, several hours based on current outdoor temperatures. So you don't have any type of short cycling of the heat pump. The heat pumps become more efficient, just like a boiler. The longer they run, the more efficient they become. They're less efficient on startup and shutdown. So that's just one given example of the functionality and the complexity of the system that you can program. Let's now go to where I created this target temperature. And that was in the mechanical iStat. And so I was calling this block, so if we go back to the DX2W and we double click on this, it's called Remote Outdoor Target. And if I go back to mechanical, I believe it is this one here. So it's outdoor target. The renaming of it was done in the callings. So this is where I'm calling it locally, what I'm calling it, but it's actually linking to the mechanical iStat and the outdoor target variable that is what you see right here, which is there's the name of it in this device. And so what we've done is we have said I want to use the maximum set point within the system, and this is a formula to convert it to Celsius because the maximum, or sorry, to Fahrenheit, because the set points are Celsius on the thermostats, but the DX2W program is using generally Fahrenheit. So I'm just converting it. I'm adding a factor, and I'll explain that in a second. And then it's again the maximum set point, take away the outdoor temperature. So you're getting a difference between the maximum desired indoor temperature and the current outdoor temperature. You're multiplying it by the maximum temperature plus a factor. To get the maximum temperatures, I start with the iNet. That is the variable or the block that I'm calling, and it's just saying max, max, max. Now, one of the things I didn't necessarily like about the programming in this control core is its max command only allows for 2 variables instead of unlimited variables. So that's why you have this nested maxes, which is kind of a pain in the butt, but if that's the worst of it, then that's not too bad. So I'm setting the max based on all of these blocks that I'm calling remotely from the 4 thermostats. And in those thermostats, the T-stats, I am creating the maximum, where is it? I'm creating the maximum set point based on all of these set points. So these are set points that you can do at the code level, or you can go to the physical device, scroll through to the zone you're after, zone 1, 2, 3, 4, and the matching actuators, and set the set points on the device themselves. We calculate the maximum set point of each iStat. We then calculate the maximum of all of the maximums, and then we are using that in the formula to compare with the outdoor air temperature and create a maximum target temperature. And I'll show you why that is so phenomenal. Let's now go to the history. So this is the history. You have the history for each device, and it is based on the settings that you made back in the iStat in this area here. And so in other words, if you haven't selected a history to keep, you will have a very short window of it. But if you have selected it, then you are able to go back many, well, for however long you've wanted to keep the history. It does take a while to update, but here we come. As we go through, it should fall through. It does. So what I specifically, let's put it on live again. And what I specifically want to show you is, let's take out, this is the cycles of the heat pump. So you can see here, it's fairly cold today. It's 8 degrees and it's not sunny. So it's a full 8 degrees. I'm not getting any solar heat gain. So 6:55 a.m. it turned off. The next one was at 7:51 a.m. So 6:55, 7:55, an hour basically on that cycle. During the day when it was warmer, at 5:54 it turned off, turned back on at 7:56. So you can see a couple of hours there. But let's get to what I was trying to show you. That's the opening and closing of the mixing valve, buffer tank temperature. So you can see it cycles on and off based on the heat pump coming on and off. Let's add in our outdoor temperature. And then let's add in the target temperature based on the formulas that I've just showed you. And now let's add in the actual mixed temperature. And what's exciting is that let me actually make this really clear. I'm going to undo that. I'm going to undo that, and you can see that these lines are basically indistinguishable from each other. They are directly over top of one another. And that has happened since I rewrote that formula. These little spots here are where I'm programming and I've lost some of the memory, and it's just data points that aren't valid. So all of those vertical lines are where the system basically has been off while I've been programming. But we can see how well that this emulates it. Now at this point, it was back on the 26th that I rewrote the program. Prior to that, you can see how the mix temperature is very, I would call it lineal. It has a lot of flat areas where it's not really responding to the outside temperatures like it is now. And if we go to put outside temperatures back on, so you can see that now it's basically a mirror image of the outside temperatures, where before it really wasn't responding quickly enough to the outside temperatures, and it was just giving us sort of directional changes on mass as opposed to minuscule changes. And if we add in the three-way mixer, you can actually see that the whole degree, the percentage that it's closed and open has completely changed in magnitude. So basically it was maxing out here at kind of 40 to 60%. Now it's doing 60, and it even goes up to 100%, where it knows it doesn't need anything from the buffer tank. So you can see a lot more magnitude to the mixing valve's movements here. And if we look at that on a very close scale, you can also see that there is a lot of flat areas in the mixing valve, meaning that it isn't cycling way above or below its requirement. It is responding in increments to the requirement so that it can move as little as possible to meet the required temperature. So it's as efficient as possible. So I found that formula in the January 2010 edition of Hydronics. And on page 15 is a formula that has been written by John Siegenthaler. And it has basically your target temperature equals your indoor required temperature plus a reset ratio times your required indoor temperature take away outdoor temperature. So fairly simple. And that reset ratio is based on the overall designed heat loss or heat load of the house at the design set temperature. So your coldest day of the year, what is the required temperature you're going to need to meet the heating requirements of that coldest day, and that sets the ratio. And then the other side of it would of course be the outdoor temperature being equal to the indoor temperature. And that would be 0 requirements, 100% of requirements. This line creates what's called a reset ratio, and that is calculated by the required supply water temperature to distribution system at design load. So in this case, we're looking at about 110. Take away the water temperature at no load, which would be 70 if it's equal to the 70 room temperature, over top of the outdoor air temperature at design load, so minus 10, take away the the outdoor temperature at no load, so again 70. So we've got 110 take away 70, 70 take away minus 10. That produces a reset ratio of 0.5. I figured out that my reset ratio, just not based on what I calculated in my design, because it looks like I may have under designed, but based on just how the system was performing, I kind of increased the reset ratio over time until the system was providing the heat needed by the house. And so it made it really easy to change. I started out at 0.3 and I've gone up to now 0.35. And now I find that I am able to meet all of the set points. So in order to look at that, let's look at a single day. I'm going to look at zone 1. So I have the temperature sensor for zone 1 and I have the set point for zone 1. And you can see that it's hovering just above and below the set point. You can see I boosted it up. This is the main room downstairs, the great room, and it's a cloudy day. So I boosted it up to 22.5 from 22 just to ensure that the system ran. The actuator was open. And if we want to add in the actuator control, we can see what the actuator's been doing. So it was off. And now it's been on since 4:08 a.m. this morning. And we can do the same thing with any of the zones. Oops, got the wrong zone there. So we can see that this one, the actuator has been off the entire time. And no matter what my set point is, it's actually been warmer than this the whole time. So I'm on the second floor, I'm on zone 2. I know that this is the zone where it's actually the iStat. So this temperature is the internal sensor in the iStat that I'm reading. It is at the top of the stairwell, so it is getting the movement of warm air from the first floor going up to the second floor. So it tends to always be, that hallway always tends to be warm enough. 3 is the garage, so we can see what that is. It went down to 8.8 Celsius last night at this morning at 6:39. And if we look at the outdoor air temperature, so it went down to 8.8. Outside was 6. So the garage is currently uninsulated, walls and ceiling, but it's maintaining a temperature that's 2 degrees roughly higher than the outside temperature. This is the downstairs hallway. Whoops, sorry, wrong buttons here. And we can see set point. It's never reached the set point. It's always been above the set point. So the actuator has been off for the last 24 hours. We go down to the main floor. This is the great room. So we've got our indoor temperature. We've got our set point. We have our actuator control. And just for fun, let's tie in the outdoor temperature in Celsius. So you can see that during the sun yesterday, 434, and even down to when did it get down? At 11 o'clock last night, it finally cooled down enough to reach the set point of 22.5. And you can see that the inside free energy I'm getting from the sun, we're at 24 degrees, even though outside it's only 14 degrees. So that's how much solar gain I'm able to get from the sun. It's quite phenomenal. And then you can see that the actuator's been off till about midnight, and then it's been on ever since. Until now, it's reached its set point, and now the actuator has turned itself off again. So you can see that the programming options here and the data that you can extract from it, and therefore the ability to program it further is phenomenal with ControlCore. This is actually a thermostat. So I talked earlier about the block type T-stat. This is where it is taking the indoor air temperature, the current indoor air temperature, the set point, your on and off dB. So that deadband means how far above and below the set point it's going to allow it to get before it acts on it. And then it's saying what it's going to do and output. So basically it's saying if the indoor air temperature reaches the set point minus the on dB, it's going to turn on the equivalent zone valve. And what it doesn't directly turn on, it is just providing a variable. And then if you, let me click on that to create these variables. So basically this is saying, is this true or false? And if it's true, it'll show that it's a lit up blocks. That then provides a true or false to the next call for the result from this block. So the next one is some further logic that's been built in. So let's go to T-stat 4. That's the downstairs bathroom. It's against the garage, so it's always cold because the garage is not heated yet and not insulated. So it often actually has problems maintaining its set point because of the fact that there's missing insulation. But if we go now to this last bit, this is a digital function block, and it's digital because it's basically acting on 0 and 1, on off kind of thing, as opposed to an analog which has multiple values that it's acting on. And it's saying mode is greater than 0, and mode in our case is indicating, are we in heating mode or cooling mode? Heating mode's 1, cooling mode's 2, efficiency mode is 3, and off is 0. So it's saying if we're greater than off, and T-stat 4, which means that T-stat 4 is true, and in this case it's true, and lockout is greater than 0. So I'll explain that in a second here. Or are we in winter cool mode and lockout is greater than 0? So this is just a further gate to determine, do we really want to turn the heat on, or more specifically, do we want to turn the actuator on? Because there's going to be times where we're turning the actuator on to actually extract heat from the room, even though we're above that set point. And the lockout I created was for the ability to do testing, because this was automatically turning stuff on and off based on the set point, and I wanted to do some testing. For instance, when I had miswired the actuators, I wanted to turn one actuator on at a time, regardless of what the set point was. So I added these variable blocks that were 0 and 1, and they would allow me to set, like right now everything's set to true. I can set it to off, and none of these actuators will come on regardless of what the set point and current temperatures are. And then I've also got winter cooling, which I've just started to program, which is going to allow me to open up a actuator if the temperature in that room is significantly higher than the set point, and the system, the overall system, so all zones, are somewhere requiring heat. And what that will do is allow the room's water to circulate, extract that energy, and take it back to the buffer tank to use for the zone that is below the set point somewhere else in the house. And that will restrict the need of the heat pump to run. So you can see, I mean, this is pretty exciting functionality that you have available to you. Again, if you can think of something to do, this is getting back to my Microsoft Access programming days. If I could think of something on how to do it, there's the functionality here to pretty much do it. There is a little bit lacking in the formulas that are available. But other than that, it is phenomenal what it can do. And there's a lot of stuff here I haven't even figured out what they do yet, like snapshots and the like. So now let's review something I mentioned earlier about dew point control. So this system is hot water or conditioned water going through the ceilings. And in the summertime, I am going to be flowing chilled water through the ceilings to allow for the system to cool down, the rooms to cool down. So chilled water will go through a ceiling. It will allow for the heat in that room to be absorbed by the chilled water and extract it from the room, lowering the temperature in the room, providing cooling in the room. But what's important is that the temperature of the ceiling is never below the dew point of the interior air. And that's where those dew point sensors came into place. And so as I mentioned, the sensors themselves, you don't have any direct access to them there's no parameter page, there's no program page, there's no history page. You have to access them via a block on a different device. And so in this case, it would have to be the iNet. So let me just briefly say that all of the devices on this COM can directly access each other's parameters. All of the devices on this COM can directly access each parameters, but the devices on this COM cannot access those, and the devices on this COM cannot access those directly. What you have to do is go up at a higher level and create blocks here that you then remotely call from these devices. And so what we've done here is we've remotely called all of the parameters that we want from those dew point sensors, the 3 dew point sensors, which is basically indoor air temperature and indoor humidity for each of those. And we then use those to calculate what the dew point is of the overall house. So here you can see the maximum dew point from the HVAC PLC. And if we go down to the HVAC PLC, which is, I think, this one here, we can see that we've remotely called the blocks that we've created on iNet that remotely called the parameters of the 3 dew point sensors. We then are creating the dew point for each of those. So we have the top floor dew point is 6.8 Celsius, the main floor is 7, and the basement is 7.2, and these are based on temperatures 22.6 and 36. Now, these aren't perfect dew point calculations because we do not have a pressure setting, but I found a formula online that is, again, I believe it was written by John Siegenthaler. This was a formula, and this is where I had to figure out how to use log instead of what the formula online was to create a very reasonable facsimile of the dew point without using the pressure setting, the outdoor barometer setting. This then was called back at the iNet so that it could be then used anywhere in the system. You can refer to this parameter anywhere else in the system. And so let's then go to the DX2W. And actually, I think it's on the mechanical iStat. So I mentioned earlier that the mechanical iStat is being used to provide additional programming functionality for the system because the DX2W's memory is already being taxed with this number of calculation and blocks. So we go back to the mechanical, and actually, I think it is in the DX2W. So again, I'm new to this. I have not analyzed what most of this does yet. And it's intense, and a lot of it's dealing with the management of the refrigerant. One thing I will show you, I had mentioned that the DX2W has internal pressure transducer that I was using as my gauge for when I was putting vacuum on the system and pressure testing the system. This is the result of that transducer, and so this was the value that I was viewing. But when we get to our target, I need to find where that's for hot water. Hot water target, where is the cold water target? I'm going to turn the program off so that I can see the names of the actual things. And I think I'm going to have to throw in the towel on how it's creating I haven't analyzed the cooling side of the system yet. I know part of it is the mixed temperature. So we have cooling mode times something. This is cooling mode is here. So if it was set to cooling mode, this would be true. Therefore, it would be 1. And therefore, it's 1 times something as opposed to 0 times something. Obviously, if it's 0, all of this would be false. But it's got min, max, dew point F, which is, I think, an SF. I'm not sure what Benoit has done for that. So we have dew point SF here, dew point safety factor. Okay, that makes sense. That's the 2 degrees we want to be above dew point. And the RPC minimum is the minimum radiant panel water temperature that we want. So there was the RPC minimum. There was the dew point SF safety factor, and then the dew point F is down here. And that's the remotely calculated dew point, which is what was calculated over here. So we have dew point max dew point in Fahrenheit. It's called dp max F. And if we go to this block here, it will be called, let's put this back onto here. It will be calling that remote mechanical iStat dp max F block. So it's remotely calling that, and it is used in the mix target formula for calculating the desired cooling temperature of the system based on the outdoor temperature and the inside temperature's dew point. And the safety factor can probably be a little bit less because there is a loss of cooling based on the insulation performance of the drywall itself. So the ceiling temperature is always going to be a little bit warmer than the cooled water inside the distribution panel. And all of this is so that we prevent condensation on the ceilings. We don't want the ceilings to be so cold that water is forming on them. So I think the last thing I'll quickly show you here is the performance of the HRV module. And so if we go to history, that's probably the easiest way to look at it. And we look at it over the week. The blue line represents the temperature feeding into the HRV module. So again, this was a module that is preheating the air, so it has conditioned water going to it. That is then being fed into the centralized mechanical ventilation system. And so the temperature coming in, which is going to be very similar to the outdoor temperature. So I select it here, and you can see it's just showing there. It's not showing for the rest of this. This is because I did not select this variable to store as a history parameter in my iNet. And so I'm only getting it based on the time that I've started to run this history graph. So that's not going to help us much, but you can see how it's dipping down at the basically very early morning, just before breakfast is the coldest time of the day, and you can see how it dips down every day. But I have been able to maintain a fairly consistent output temperature of 20 to 21 degrees, even up to 22 degrees, which is phenomenal. This is getting untempered water from the buffer tank. So this does not go through the mixing valve, which is why you are seeing these frequencies. This is matching the buffer tank's high-low allowable temperatures based on the heat pump being on and off. But you can see with just a little bit of hot water going to this coil, we've been able to pretty much consistently have the incoming air pretty much at room temperature. So what that means is that the supply ports that this air is coming out of into certain rooms, that air is at room temperature and it's not chilly. It's not creating a cold inflow of air. So I think that this is getting a pretty long video. I think that's it for this video. On future video or videos, I will go through some specific programming of the DX2W to show how we're able to affect the efficiency of the system. I'll go through the BTU monitoring, so you can have monitoring of individual circuits. For instance, in a multifamily, you can monitor the usage by each unit by calculating the flow of the circuit feeding that specific unit and the return temperature and the supply temperature and all that kind of stuff. So I'll go into all of this in a future video. And in the meantime, thanks for watching. And if you like our videos, please subscribe. Please give us a thumbs up and hit the bell icon so that you're notified the next time I do upload videos. I do not upload videos on a consistent basis, so the bell will really help let you know when I have put out content, if that is of interest to you. Thanks and have a great day.